Hi students, I'll try in this educational video to technologically introduce how to determine the wind pressure applied on a building vertical wall or on a building roof based on Eurocode 1 standards, of course, as simply and as clearly as possible. Okay, let's go. First of all, some basic notions about wind flow should be assimilated and properly taken into consideration when determining the wind pressure. As it is depicted by the figure that you see now in this slide, if we consider a wind flow blowing against, let's say, the front side of a building, the wall of this front side is called windward wall, and the wall of the rear side is called leeward wall. And as it is depicted by the plan view, the wind flow is separated across the side wall, and also it's separated across the roof as it is depicted by the elevation view. It's to note also that two wind directions are considered as it is depicted by the figure that you see in the right of this slide. The first wind direction is called theta equal to 0 degree, and the second wind direction is called theta equal to 90 degrees. The wall or the dimension of the wall on which the wind is directly blowing is called crosswind breadth, and the dimension of the wall parallel to the wind direction is called in-wind depth. And as you can notice, the crosswind breadth and the in-wind depth are variable depending on the wind direction. Now I will talk about the wind pressure applied on wall and roof surfaces. So based on the model that you see now in this slide, we have external pressure and internal pressure. The external pressure is acting on the outer side of the wall and the outer side of the roof, while the internal pressure is acting on the inner side of the wall and the inner side of the roof. The external pressure is considered positive when it pushes the wall and the roof towards the inside of the building, and it is considered negative when it pushes the wall and the roof outside the building. Now for the internal pressure, it is considered positive when the opening is carried out in the windward wall, and when it is positive, it pushes the wall and the roof towards the outside of the building. And when the opening is carried out in the leeward wall, the internal pressure will be negative, and when it is negative, this means that it pushes the wall and the roof towards the inside of the building. Now, if we consider a wall or a roof and we have an external pressure applied on this wall and an internal pressure also applied on this wall or this roof, the global pressure applied on this wall or this roof is equal to the external pressure minus the internal pressure. Don't forget the external pressure and the internal pressure can be positive or negative. Now I'll explain how to determine the wind pressure applied on external and internal surfaces. So based on Eurocode 1 standards, we can determine the wind pressure applied on an external surface denoted by WE as a peak velocity pressure denoted by QP evaluated at a certain reference height for the external pressure denoted by ZE multiplied by a certain pressure coefficient for the external pressure denoted by CPE. In the same way, we can determine the wind pressure applied on an internal surface denoted by WI as the peak velocity pressure QP evaluated at a certain reference height for the internal pressure denoted by ZI multiplied by a certain pressure coefficient for the internal pressure denoted by CPI. So the question is how to determine the reference heights for external and internal pressures, how to determine the peak velocity pressure, and how to determine the pressure coefficients for external and internal pressure. Well, for the reference height for the external pressure, we have three cases. The first case is when the height of the building, denoted by H, is lower than the depth of the building, denoted by B. In this case, we have a single reference height, ZE, equal to H. In the second case, when the height of the building is between the depth of the building and 2 times the depth of the building here in this case is considered to be two parts. The lower parts is extending upwards from the ground by a height h equal to b, and the upper part is consisting of the remainder. In this case, we have two reference heights for the external pressure, ZE equal to B and ZE equal to H, as it is depicted by the figure that you see in this slide. The case 3 is considered when the height of the building is greater than 2 times the depth B of the building. So in this case, the building is considered multi-parts. We have the lower part, which is extending upward from the ground by a height equal to the depth B, and we have an upper part which is extending downwards from the top by depth or by a height equal to the depth of the building B, and we have an intermediate part between the lower and the upper parts, which can be subdivided into several strips. So as you can notice, in the third case, we have several reference heights for the external pressure. We have the reference height ZE equal to B, and we have multiple or several reference heights ZE equal to Z strip, depending on the number of subdivision associated to strips, and we have a reference height ZE equal to H, as it is depicted by the figure that you see in this slide. Well, this is for the reference height for the external pressure, denoted by ZE. Now for the reference height for the internal pressure, denoted by ZI, it's equal to the reference height for the external pressure, ZE, on faces contributing by their openings to the creation of the internal pressure. Now I'll try to explain step by step how to determine the peak velocity pressure. So based on the Eurocode 1 standards, the peak velocity pressure is determined based on the formula that you see now in this slide. And I will try to explain each component that appears in this formula. I start with the wind turbulence intensity at the height Z, denoted by IV, which is equal to the standard deviation of the wind turbulence sigma v divided by the mean wind velocity Vm, and after simplification it's equal to the turbulence factor K1 divided by the orography factor C0 multiplied by the natural logarithm of Z, which is the height, divided by the roughness length, denoted by Z0. This formula is valid when Z is between Z minimum and Z maximum. Here, Z minimum and Z0 are determined based on the table that you see now in this slide, depending on the terrain category. And as you can notice in the formula, when Z is lower than Z minimum, the wind turbulence intensity IV is equal to IV evaluated at Z minimum. This means that we will replace Z by Z minimum in the formula of IV. Well, now for the standard deviation of the wind turbulence denoted by sigma v, it is expressed as a certain terrain factor Kr multiplied by the basic wind velocity Vb multiplied by the turbulence factor K1. And here the terrain factor Kr is obtained as 0.19 multiplied by Z0 divided by Z0 associated to the terrain category 2. Don't forget, Z0 is obtained using the table 4.1 in Eurocode 1 standards. And here, the turbulence factor K1, the recommended value of the turbulence factor K1 is equal to 1. And for additional information, you have to examine the bridge standards associated to the European standards 1991-1-4 national annex. And for the basic wind velocity, it's expressed as a certain directional factor C there, multiplied by a certain season factor C season, multiplied by a certain fundamental value of the basic wind velocity VB0. And here the recommended value of the directional factor is equal to 1, and the recommended value of the season factor is also equal to 1. For the fundamental value of the basic wind velocity, it's determined based on local wind maps. And as Tunisian, I suggested the local wind map of Tunisia. And for each country around the world, you can find a local wind map with different wind zone. And for each wind zone, you have a fundamental value of the basic wind velocity. For the mean wind velocity denoted by Vm, it's equal to a certain roughness factor Cr multiplied by the orography factor C0 multiplied by the basic wind velocity Vb. And the roughness factor Cr is expressed as the terrain factor Kr multiplied by the natural logarithm of the height Z divided by the roughness length Z0. And this formula is valid for a height Z between Z minimum and Z maximum. And here I forgot to mention that Z maximum is equal to 200 meters. And for in the case when the height Z is lower than Z minimum, the roughness factor CR is evaluated at Z minimum. This means that we can use the same formula when Z is between Z minimum and Z maximum, except that we replace Z, the height Z, by Z minimum. And the orography factor C0 is taken as 1 unless otherwise specified by the clause 4.3.3 in the European Standards 1991-1-4. Now, if we come back to the formula of the peak velocity pressure, denoted by QP, we notice that it can be determined also as a certain exposure factor, CE, multiplied by a certain basic velocity pressure, QB. The exposure factor is determined based on the chart that you see now in this slide, depending on the height Z and the terrain category, and the basic velocity pressure QB is expressed as 1/2 the air density multiplied by the square of the basic wind velocity. Now I will explain how to determine the external pressure coefficients for vertical walls. So if we consider the plan view of a building and the wind is blowing in the indicated direction, so as I explained before, B, the dimension small b is the crosswind dimension, and the dimension small d is the in-wind dimension, and we consider a dimension small e equal to the lesser between the dimension b, which is the crosswind dimension, and 2 times the height of the building. So as you can notice, the dimension of the side wall is small d. Examining the elevation view, 3 cases can be distinguished for the pressure zones in the side wall. The first case is when the dimension small e is lower than the dimension small d. In this case, we have 3 pressure zones in the side wall: the zone A, the zone B, and the zone C. And the pressure in the zone A is higher than the pressure in the zone B, which is higher than that in the zone C. and the in-wind dimension of the zone A is equal to the dimension small e divided by 5. The in-wind dimension of the zone B is equal to 4 divided by 5 multiplied by the dimension small e, and the in-wind dimension of the zone C is equal to the dimension small d minus the dimension small e. And as you can notice here, the elevation view depicts a building with a flat roof and also a building with a duopitch roof. The second case is when the dimension small e is higher than the dimension small d. In this case, we have two pressure zones in the side wall, the zone A and the zone B. Of course, the pressure in the zone A is higher than the pressure in the zone B, and the in-wind dimension of the zone A is equal to E divided by 5, and the in-wind dimension of the zone B is equal to the dimension small d minus the dimension small e divided by 5. The third case is when the dimension small e is higher than 5 times the dimension small d. In this case, we have only one single pressure zones in the side wall, which is the zone A, and of course here the in-wind dimension of the zone A is equal to the dimension small d. Well, notice that we have three types of vertical walls. We have the windward wall, denoted by the letter capital D, and we have the leeward wall, denoted by the letter capital E, and we have the side wall with its pressure zones, ABC or AB or A, depending on the case. So based on the table that you see now in this slide, you can determine the external pressure coefficient depending on the zone and also depending on the ratio h divided by small d. Small h here is the height of the building and the small d is the in-wind depth dimension. And notice that we have for each zone two types of external pressure coefficient. We have CPE 10 and CPE 1. CPE 10 is the external pressure coefficient for a loaded area of 10 meters square, and CPE 1 is the external pressure coefficient for a loaded area of 1 meter square. And you can determine the external pressure coefficient for a loaded area between 1 meter square and 10 meter square based on the figure that you see in this slide. And finally, you can determine the global CPE in the considerate phase as an area weighted average of the different CPE in the different zones as it is indicated by the formula that you see in this slide. Now for the external pressure coefficients for duopitch roofs, and the duopitch roof is indicated by the figure that you see now in this slide. And as you can notice, the angle of the duopitch roof can be positive or negative, here the angle alpha. And based on the direction of the wind, we can obtain the pressure zones for the wind direction theta equal to 0 degree and the pressure zones in the roof for a wind direction theta equal to 90 degrees. And based on the table that you see now in this slide, you can determine the external pressure coefficient in the roof depending on the pitch angle alpha and also depending on the wind direction theta. Of course, all the figures and the tables are extracted from the Eurocode 1 standards associated with the European Standards 1991-1-4. It's to note also that external pressure coefficients for other types of roof such as flat roof, monopitch roof, hipped roof, multi-span roof, and vaulted roof and dome can be obtained based on the European Standards 1991-1-4, of course associated to Eurocode 1. Now I will explain how to determine the internal pressure coefficients denoted by CPI. This CPI is dependent on the opening size and also the opening's distribution. And when determining the CPI, we have two cases. The first one is when the building is with a dominant phase, and the second one is when the building is without a dominant phase. It's to note here that the phase is considered dominant if the area of the openings in that phase is at least 2 times the area of the openings and the leakages in the remaining phases. Well, in the case of building with the dominant phase, if the area of openings in the dominant phase is equal to 2 times the area of openings in the remaining phases, the internal pressure coefficient CPI is equal to 0.75 multiplied by the external pressure coefficient CPE evaluated at the pressure zone containing the openings in the dominant phase. If the area of openings in the dominant phase is higher than 3 times the area of openings in the remaining phases, the internal pressure coefficient CPI is equal to 0.9 multiplied by the external pressure coefficient CPE evaluated in the pressure zone containing the openings in the dominant phase. And when the area of openings in the dominant phase is between 2 times and 3 times the area of openings in the remaining phases, a linear interpolation should be used. It's to note that if the openings in the dominant phase are located in zones with different external pressure coefficients, in this case we should use an area-weighted average value of CPE. Now, for the case of building without a dominant phase, the internal pressure coefficient is determined based on the chart that you see now in this slide. And as you can see, the internal pressure coefficient CPI is depending on the ratio H divided by D. H here is the height of the building and D is the in-wind depth dimension. And also CPI is depending on a certain coefficient mu equal to the sum of the area of openings where the external pressure coefficient CPI is negative or 0 divided by the sum of area of all openings. If for a reason or another it's not possible or not considered justified to estimate the coefficient mu, in this case the internal pressure coefficient CPI should be the more onerous of plus 0.2 and minus 0.3. This educational video takes end. If you have any questions, remarks, or suggestions, please mention it in the comments. Thanks a lot for your attention.